All right, so let's wait for Seth. All right, so where's everybody? You know, days that there's no CP, like half the class doesn't show up. And then you put in your survey, why do you have CP? Because I want you to be here so you can learn. All right, it's okay though, no CP for today because we have enough things to do in person. We don't get time to spend time on CP. All right. So last class we ended with like at the beginning of the MATLAB toolbox, right? So hopefully everybody submitted their class participation, and that was just the extension of what I was doing in class. So hopefully everybody done the class participation. And today I'm going to show you 3 other ways of tuning your PID controller. All right, so you could always just do it through your script if that's what you want. There are 2 other ways. If everybody wants to listen to me when I talk, that would be really nice. Ian, I'm talking. So 1, you could use MATLAB toolbox. So you will use the whole GUI or GUI. You say GUI or GUI? GUI. And you can move some sliders and then look at your graph and see how it looks like. The other, you can use MATLAB tuner inside your code, get the coefficients. Either method you use, you will decide how the response should look like. So MATLAB will do a approximate of what MATLAB thinks the system should look like, but MATLAB doesn't know the system specification. So you will be the engineer that you will evaluate the response. And then if change needed, you apply that. Okay, so using a MATLAB toolbox doesn't mean, oh, my life is a lot easier. No, just the part that you guess the first round of KI, KP, KD will be a lot easier because MATLAB will do it for you. But that's the rest is iteration and interpretation and trying. There's not a final answer. All right. So instead of going 100, 210 for the 3 values, MATLAB will give you like 56.3. That's just the only difference. All right. So by no means doing your homework, you just use this one time and submit. You have to look at the specification of your system. All right. It's reiterating this because I've seen the first iteration submit, oh, MATLAB told us that's the values. So the command for PID tuner in MATLAB control toolbox is PID tuner capital T, and then you put your system in the parentheses, comma, if you know what kind of a controller you're designing. If you didn't, you have no idea what's going to be, and you just want to see the response for now, you can eliminate that type, just say parentheses system, whatever your system is, close to parentheses, you run this, the GUI will open, and then you have access to the type of controller inside. Then you can go, let's try P, let's try PI, let's try PD, PID, there are so many other things, okay? So if you already looked at the first response and then say, oh, I think I need PI, then you will put PI and MATLAB will give you 2 variables, KP and KI to start with, all right? You will see some window like this, and I'm going to show you the lecture slide, and then I'm going to go on MATLAB and pull that up, and you'll work there. So we're going to work on the example that we worked last class. So you already know how it looks like. You have tuned the PID controller a little bit, so you're familiar with that. And I'm going to use the same code. I just added 1 line for the PID tuner to pop up. So again, for this purpose, the only thing I'm going to check is if the system looks stable, right? And then for the next example I show you, there will be some design specification. So that's one way, using MATLAB toolbox. So you create your system in the script, right? So you have a transfer function, numerator, denominator, whatever method you like to create your system in the script, run, then PID tuner, open the tuner. You could also go from Simulink, because if you have a transfer function, you can create the Simulink file of that, right? So transfer function, feedback control, and then you can put a PID control block. from the library before your plant, then if you double click on the plot, you will see on the PID controller box, this will show up. And if you click here, tune, it will take you to the same place, MATLAB toolbox. So both of them will take you to the GUI. We're going to work on both of those today. Now, the only difference is if you are going from the Simulink, you can give some initial values like 111, 1.01, so something to start with. And then you go tune, it takes you to the toolbox. All right. So for both of these, you will see this window. Just getting there is different. One is through the script, one is through the model. All right. Let's see, what do I have here? Then you'll plot something and there are ways to change. So you will have two sliders. That the first one is the response of a system. The second one is if the system is more aggressive or more robust. So one is the transient behavior of the system. One is the time response. So you basically just slide these two and then you observe in the same time what's happening to your system, and then you just say, oh, I like it like that. Then you can hit this box, show parameter, check all the parameter of the design. We'll go there and see. I just want you to know there are these three that are important. Once you're happy with the response that you have, you say update the blocks. Now, if it's in Simulink, it will update your controller. If it's in your code, you want to export it to your script. So it will create KI, KP, KD that you've got here. All right. So this is just the trial error part, but it's more user friendly. So as soon as you change something, you observe it. So you don't have to run step function every single time. So this does the step for you at the same time that you are changing things. All right. So let's do this. I'm going to stop sharing because I have to share my MATLAB. Just make sure. Katie, do you see MATLAB code on the screen? For the purpose of recording. Okay, I'm going to reshare and be sure. All right. So this is from the previous code. I'm going to run. So if you remember we had the transfer function. I'm going to show you the step function, and then we're going to see it in the toolbox. It's the same thing. So, so step function in the toolbox, you'll see it with the controller. So this was our step function. We didn't like it. What did we want to do? We wanted to use a PI controller, right? To get rid of the steady state error and make sure that we get to the final output, which we were tracking step, right? So we wanted to get to 1. Do you remember this from Monday? All right. So if you go to command window, I got the step info, right? Time, rise time, transient time, settling time. These are the items that I need to check versus my design spec, right? Now in the GUI, you will have access to all of this, but in a different way. So I'm going to close this and then run this line, which is PID tuner, and P is my system. It's not a P controller. It's just a bad naming. Let's just fix that. Because then if you are just so you're not getting confused, let's do that again. Sorry, I should have thought about it before. Okay, now I'm going to run PID tuner sys. I don't know what kind of control I'm going to use. It's all right. This is the toolbox PID tuner. So this is the step plot reference tracking, because I'm tracking the input and I want to know if my system is tracking 1. So here you see in the type that MATLAB is assuming a PI controller. That's MATLAB's default for PID tuner toolbox. If you don't mention what it is, it always assumes a PI controller because it thinks that there will be some steady state error. I'm going to get rid of it. All right. It might not be the correct controller for you. So you could, for example, change and say it's a P. All right. Now, for a P controller, since you are just changing the gain, you'll see that you can only adjust this time response. So I'm gonna make the system slower. So you expect it to be to reach to that steady state value slower. And if I make it faster, so the time response from 10% to 90%, that's gonna be faster, right? But you'll see that this does not help you with that steady state error. So you know you would need either I term in there or something other than just P. So let's go with PI that MATLAB suggested or as default it has. Now things that change, you can now change the transient behavior. So you can either make it more aggressive, so faster, or you can make it more robust. So let's change the system, make it system faster, and then improve some of the transient behavior. Yes. So when you have robust, you are not introducing too much of oscillation to your system. When it's aggressive, you're putting your poles kind of closer to the, you're adding some big term of integral. So your pole, the pole that you'll be adding from your controller will be closer to the vertical axis. So you're going to introduce more oscillation, but you know you're going to get rid of the steady state error because your integral term is stronger, right? But we don't always need that. So you don't usually need to be all the way aggressive or all the way to the robust that, hey, let's treat this very carefully. You can be somewhere in between. Now, you can change the numbers here also, so if you want it to be so close, like change these smaller if the slider was not good. So I know that I need to get to 1 because I was tracking 1, right? So this is kind of trial and error for you to play with. So making it more aggressive, but I'm pushing the system toward faster, right? A response. Then I have to change this a little bit. Then like you just basically have to play with this too. Now let's say you get to a response that you're happy with. All right, now you want to know what is the KI and KP because you don't see KI and KP. If you go to show parameters, you're gonna see your KP, your KI, right? And then you didn't have KD and TF for now, you don't have to worry about that. Yes, that's the cool part. That is the step info information. So if you wanted your rise time to be less than 2 seconds and your overshoot, wow, that's 26 a lot. Let's say your requirement, design requirement is rise time less than 2 seconds. So they, yes.
So if you were to put the KPI,
yes, it will be the same in the step response. Yes. So this is kind of the trial error for you. So visually, because changing KI, KP, you might not understand, okay, how do I know I have to say KI instead of 1 is 1.5? But when you see the response, it visually helps you better because that's in time domain. Once you're happy, you can go and say, okay, what was the KI for this? So MATLAB behind the scene is solving the whole thing. Every single time is running that block diagram, solve the equation, do the step, just shows you the step. Now, let's say that your requirement was rise time less than 2 seconds and overshoot less than 10%. So you made one happen, the other is not. So now you have to go and change the overshoot, reduce. Now you have to go and check, which one of my controller will help me to reduce my overshoot, right? Maybe PI is not going to be your solution. Maybe you have to use a PD controller. Or with PD you couldn't, maybe you have to use a PID. Now, if that is the case, let's say that we couldn't do it, and then we have to go use a PID. I'm gonna click here on type and see, I can choose PID. And then, okay, this is PID, let's check the parameters. So less than, it's not less than 2 seconds, but overshoot is less than 10%, right? So you just have to, so the system has to go that way, right? For faster response. So I know my response has to be faster. Let's see. So it's less number here. So change 1 and then go check your parameter again. So I have less than 2 seconds and 8%. So anywhere less than 2 seconds is acceptable, right? Now, which one you accept? Like KP right now, 94, KI 296, probably too big. KD 6.7. So let's say your KD was 6.6 or 6.5, you would still meet this requirement. Where do you stop tuning? Where would you stop tuning? That's a good question, right? Because you can design so many controllers and like how far I can go. Yes.
Based on your budget.
One is you have to look at the project, and the other, let's say that you don't know the budget yet, right? So let's say it's time less than 2 seconds. So you have a value 2, below 2 is fine. 1.9999 is also below 2, right? And then overshoot less than 10%. 9.98 is also less than 10%. But 8% was also less than 10%. So how far, because the rest is just looks good, I'm just tuning it more. But tuning it more, like where would you start? What is your criteria to decide what is a good controller? And you're just designing, you don't know the money yet. Then yes, that's always consideration. Like for me, that I was like, I'm doing too big. I probably wanna revise that. I'll probably design it 2D for this one, maybe. I don't know. But where would you stop for this PID? With rise time of like if your condition is 2 seconds, below 2 seconds, 1.99 a good number, or maybe like 1.8. Both of them are because your requirement was below 2. Your answer is right, but your reasoning is wrong. Satisfactory is not the reason for that. Your choice was correct.
Did you just add as needed?
What do you mean by choose as in control?
Like before you get to the full PID, like try PID.
Yeah, let's say we went all of that and spent 2 hours. I'm not kidding, 2-3 hours just to tune a PID controller. And then after 2 hours, like, okay, I'm gonna decide on something, right? And you are kind of in the good area. This is green area. But how far you want to go? Now, sometimes you want to be perfectionist, like we are perfectionists. We want to just pick the best one, right? Where do we stop? What can you elaborate that? So the budget, like so if you expect your system to be so fast, too fast, means that, okay, this has to handle this RPM. If not, you're gonna see the magic smoke, right? If you're giving a big gain, the motor, let's say, has to tolerate or be able to accept a high current. If not, you're gonna see the magic smoke, right? That just means the beefier motor. That's correct, right? But then the example between 1.98 and 1.8, they're both below 2 seconds. They're kind of the same neighborhood. Would you design, so let's go maybe with filters. Let's forget this. Let's say you're designing a low pass filter or high pass filter. You have a cutoff frequency of 60 hertz. Are you gonna design your filter for exactly 60 hertz?
No.
So why? What would you do?
Decided, you know.
So you assume a threshold, right? Why?
Like,
So first, we are not living in ideal world. Second, do you remember system sensitivity? There might be something in system that makes a system sensitive. So if your system's environment, there's a little bit of noise, you can throw it off, right? So that 60 hertz, because of something might not be 60, like you're having something like 65, just because there was some noise in the environment, let's say. Here the same. There might be something from the environment or some of the linearization you have done, right? All of these are estimation, like this transfer function we write, they're all kind of like, you're making a nonlinear system linear, right? They're all LTI, agreed? Most systems are nonlinear. So we are estimating. Now, as engineers, you have to come up with a good percentage of, so you can't say just like, okay, I'm gonna design 50% over what the spec, no. You go to where you're supposed to, that you have the green line, right, below expectation, specification. And then you assume this much threshold, maybe 2%, 1%. So maybe you design it for 1.8. And then you also give the design for 1.9, you check the price for both. If the price is not too big, you will suggest as engineers that 1.8, because you want to make sure that there's a leeway for the system never go unstable or always meet the requirement, right? So when you're tuning, if I said 2 seconds, don't try to be 2 seconds or like 1.999. That's not a perfect design. Make sense? Going like 1.9 is good, and then you'll explain. 1.9 is that this many percent below the expectation or the below the spec, you're good. So a lower is not always bad, yes. I don't know, depend on your system, your project, your system sensitivity, so you need to do a little research. What is the common engineering in your field, in the field that you're designing controller for? They all decide how much. For our assignment exams, if the condition was 2 seconds, go maybe like 10% below, like really your judgment. Whatever you put, you'll explain why. So if you go with 1.6 below 2 seconds, right? You'll say that I assume this much threshold and the tuning was not difficult.
I just remember when I was those on the opposite spectrum that you gotta make sure it's realistic as well. You can't have a ride on one spectrum.
Yeah. Yeah, that's the magic smoke. So you can't have the system too fast. So let's say it's 2 seconds. You're saying that, okay, I want it to be 1 second. Just want to make sure the system is awesome, is 150%. Like this is over designing, right? But nothing is gonna happen in the system. But that just translates into buying a more expensive component, or the current component would not tolerate. It would just break. So the design choices in designing controller would impact the whole system, right? So because when you're designing a controller, you're the control engineer, design something. These are all digital control, right? They're not analog. The digital control is all code. And then you ask your mechanical engineer or the person that's in charge of procurement, hey, buy a motor that can tolerate this much voltage and this much current because I designed this controller. And they said, okay, the budget is $1,000. I'm gonna buy a motor that's $800 and it's gonna satisfy you. But you could have designed a controller that only needs $200. Does that make sense? So it's both ways. So you cannot over design for something that's too beefy, too big, too assured that it's not going to fail just because on the paper it looks good. It can mean more expensive component. You should not also design something that barely satisfies the requirement because easily can go overboard. The engineering intuition, the engineering experience is what fills between this blank, like where you stop, a little bit of common sense, a little bit is the system you're working with. And that's why engineering is beautiful. Every one of you will design something different and they're all correct. But as long as you have a reasoning for what you design, they're all correct. All right. So for now, don't be worried too much about like, oh, where do I stop? As long as you're not trying to go for perfect 2 seconds. All right. Because it's very difficult to like get that timing correct. And again, these are digital control. So there's a lot of losses of signals and whatnot in the system that the actual system might not be like that, Wilson? Yes. Do you remember when I said, what was it? Okay, can you fall back to? I forgot, it was very important. Yes.
You know, if they're kind of schools out there, where I'm just thinking like, certain values you get certain performance and it's like certain performance from that. You did perform. But I want to know a right and then you're like
What's that? Yeah. Oh, remember, thank you. That was a good break. So all of this are in the paper, right? Wilson, you're not allowed. You could have just fallen asleep and I remember. Once you get these numbers, you have to apply to your system. So digital controller type and microcontroller, whatever your computer is, right? Run, measure things, and then measure the time of 10% to 90% of the performance. Is it still the right time that I wanted? It might not be, because real system has other losses and things that you linearize and you didn't consider, right? So even everything looks perfect on the paper and in the simulation, these values might not be your final. They are one step before being final. You have to apply to a system, so code, and then run voltage generator or current, like a signal generator system. Oh, let's look how it looks like. It took more than 2 seconds. So then on the hardware, you will tune. That's the refinement idea. That's what I was going to say. So tuning has like few steps, one full theory, then go to simulation and then try to find the common sense. Then hardware in the loop and make sure that it still satisfies all the requirements. And the reason is because all systems, almost all systems are nonlinear. To use all of these methods, we are linearizing them to be able to use LGS. So a lot of things will go, unnoticed. And it's fine because it helps us, right? To get very close to what we want and then just choose it. So we need that human interaction. Now, there are tools that you can say, let's say, for example, I want my omega n or my damping to be this value. You can plot between good locus, you can actually have that and say, oh, if I put my pulse in this area, that's only going to get that omega n or that damping ratio. Okay, but still, you have to do it as human, right? You can code all of it and it does it for you. You can write a machine learning using genetic algorithm and tune your PID for you. Grab that, run your system. So you cannot eliminate you because there is a hardware to do. But you can use genetic algorithm to do what you want. It does. It's actually a very cool video about that. I will post that for you guys. All right. So, do you want to play with this a little bit? Open your MATLAB online. Run the same code while I bring up the Simulink code because it takes forever to load. Okay. You did not save it. Great. Well, you submitted as CP, so you have it somewhere.
Oh, I have all that. I just need to put the same line in.
You only need to create the system though. Then PID tuner system, open that toolbox. You basically need this. Here, write that. These two, and then PID tune says 3 lines of code. Wait 10 seconds until this cooks, and then you can just move the slider up and down, like back and forth, and see what happens. Check the parameters, so just become familiar with that. There's also on the far right, if you click on update block, if you instead of that click on the arrow, you can see there's export to the workspace, so you can save those there. Yes.
What is the fastest time you've ever done this on a real project?
Fastest time, it was gruelingly slow, and we ended up just saying, you know what, it was our vehicle underwater, we went to the pool, change, send it, no, bring it up, open, change, it was bad. Don't like tuning PID controller. No. So no, not having a fun time doing that. Sorry, no good news for you. 4 examples that I will give you is quite fast because they are all built systems, they are not real life scenarios. So it's easier, less time consuming. And usually you can, there are methods to get a very good educated guess, but for real systems, it's more difficult. You always have to compromise or just estimate something and then go to the hardware and find the value. Do you have a project that needs PID tuning? Good luck. So I'm going to pull up the Simulink example while you're playing with that. Yes. There is none. You check your project versus. So, it says if your system is in general a slow system, for example, the underwater one we have, it's super slow. At the fastest it goes is 2 knots. The fastest. And you are happy to have that. And that system is slow. So right sign. Oh, it takes for 10 seconds. I don't care.
I was thinking.
So, for that, I didn't give you a number, but you'll see that for your homework, there's a number for the second. So that was more of like how do you like make it faster. It's really, you didn't have any criteria. So it's more, oh, look at that. I could open this guy. No. All right, so. Okay, instead of, are you guys working on it or are you just talking? Don't get distracted. These minutes are really important. If you don't have a computer, it's fine. You're gonna move to the next thing. You have to do it when you have access to a computer. I cannot reiterate how important it is. You do this yourself. This part of the lecture is not you listen to me very well, you learn. You have to do it. Even doing the same example will help you. All right. Now, was there a question before I go to the next thing? No. All right. So that was one way, right? You could use a script, run a script for a system you have, and then you try to tune based on your requirement. The other way is using Simulink. So if you run this, don't do it now because it's going to take forever probably for you to come up, but do it at home. This is a example from MATLAB MathWork. If you run that, here you have requirement. The goal is to design the system to track the reference signal, and then the settling time has to be under 2 seconds, okay? And then 0 steady state error. So you are eliminating the steady state error. There are 2 conditions or the design condition. Now let's go and do that. So I already uploaded. Now this is the whole system. This is your step input. This is the engine speed RPM. Let me check this PID because I opened it recently. Okay, that's one. Let's just run it. Using OD45, MATLAB is solving it. Okay, so when you're working on this, open all the blocks and see what's inside. Okay, but for now, we're just using the PID controller box. So this is a PI controller. That's what was there. You could have started PID or P, whatever. You choose here, parallel form, which we already established that. So here the value for P and I are given to be 1, just easy, because it's the first iteration. You have no idea, you just want to run. It just means that it has a PID block in there, right? Now, if we click on tune, it will open the tuner for us, right? So it takes us back to where we started. It does not. Why? Apply, not tune. Very sensitive. Okay, compiling all of that. All right, so let's check the parameter before we do anything. Bless you. So it did change the P and I a little bit because we opened the tuner and it's like, I'm gonna tune it a little bit the way that I want. So basically eliminated the overshoot here, if you notice, and then there's 0 steady state error. So rise time 0.349, overshoot of 2.46. What was our requirement? 0 steady state error and less than 2 seconds, right? So, well, that tuned very well. Let's mess it up a little. Ah, great. Now let's check. All right, So let's say overshoot was 25%. Then from here is the same thing. You go back and change the values. Couple of things that I want to show you on this, you can stay down here, is one type of controller you can change. It's very slow. Okay, whenever it decides to open. So this shows both frequency and time domain controller. So here you see that your domain is time. You also could have frequency domain. The response of a system in frequency domain is called Bode plot, right? We're gonna cover that after exam. So for now, we're just staying in time domain. So in time domain, the controller we have, this is supposed to change, but like it did, I don't know, for some reason it's frozen because it's probably doing something. PI, PID, all right, the RPIF, that's, you can be in time domain, but you have information about a frequency, you can use that in tuning your controller. You're not doing that yet. We'll do that once we cover the frequency. So you will see more option for controller that I introduced to you. Only use the one that you know. PI, PD, and PID. All right. The rest of them we'll cover later. You can also here export to the MATLAB workspace. Your KI and KP and KD will get exported once you're happy. Now let's say that we tune this and the values are what we really like. Yeah, we don't like that. So let's say this is what it was. Update blocks. So it updates the blocks in your Simulink. Now, if you run the Simulink now again, I forgot to run it before changing the controller. It was not stable. So when you're doing at home, do that. And once you update this, your response of your closed loop system in Simulink would look exactly what you expect. It will get rid of all the noises, and then you're tracking your input signal. Let's say we did that, close this. Here, this was the tune, so we have to say apply. Okay. Now, if I run, then I should have showed you this before this was tuned, but this is the scope, right? So before there was some noise here, this wasn't at 3000. Using that controller, there's a little bit of overshoot, which is fine, but it reached the 3000 because the 3000 was whatever the input in that was, right? So when you run, check this response first and then change the controller and then check again, you'll see the difference. So this is the second way of tuning controller. The third way is if you do it through the script. So completely, you don't even open basically don't open the GUI, the toolbox. MATLAB still has a command that does it for you. So you can use PID tune command system. And if you know the type here, you need to tell the type, right? PID. So for example, I build my system. I say that, hey, put the information for the PID controller in this vector, use PID tune for this system, and I'm designing a PI controller, okay? If you run this, it would, actually I can run it here. It will create, I need to close this guy, no. Here, that example. So let's run this, run in advance. So it created the KP plus KI1/S controller, and it used KP and KI values for it. Again, this is just something that MATLAB thinks the system is stable. It might not meet your requirement, your design requirement, right? Now to do that, to check if it meets the controller, because MATLAB only designed the controller. It didn't put it in the system. You are going to get the feedback. So controller times plant in a feedback loop, you get the closed loop system transfer function, get the step function, and then observe how does this step function look like? Now, if this, for example, if I right click, rise time, click. If this rise time was whatever, if I'm happy with, I can stay with what MATLAB gave me, right? 2.35. If my rise time needed to be under 2 seconds, so the values MATLAB gave me was not good, but I have a good start, right? So all of these gives you a very good start, educated guess for tuning your controller. Instead of let's start from 100 and then 200, 3, 4, 5, let's see what happens, like how lucky I get, right? So all of these are helping you with tuning. And PID control tuning is the hard part. There is one other way. And is there any question for these ways that I talked about so far? Yes.
So when we're doing the, PID, if it is not your parameters, how do we choose that?
Which one? The one with the GUI?
The one that shows.
This one?
Yeah.
So you have the KI and KP value, right? So you start in your script. So you remember we already did it like manually, right? So your KI here was 36, let's say point something, and it didn't give you, but you know it's around 36. So make it 35. And then what's the block? So it's KP plus KI over S, right? This block times your transfer function feedback gives you, so you have the code from that, from the CP. So change that KI to a different value that's close to what MATLAB gives you. Look at the response. Does it get better? Does it get worse? If it gets better, go toward that number. If it gets worse, get away from that number. But it's around that neighborhood. You have to do that refinement, like no matter what. Like you can't have a code unless you use machine learning to do it for you, which is going to do the same thing and check versus the prime. Just getting you closer to what you would end up with. Okay. Any other questions? How tired is everyone? It's only Wednesday. So this is when I give you my speech. Okay, welcome to my speech. When you go to work, some of you are already working. Wednesday is just like Monday or Friday. It doesn't matter. You're working 8 to 4 or 9 to 5. Every hour of that, you have to be fresh. You have responsibility. So I'm tired, it's 3 o'clock on Friday. It's not acceptable. So try to learn that culture while you're in school, because you can't afford falling asleep, not paying attention. But when you're working, you cannot afford that. 2-3 times you do that, either getting fired, not getting promoted, being yelled at, getting the really bad emails from the boss. Okay, so it's the best time in school to learn that. But Saturday and Sundays are yours when you work. So we have 10 minutes. Okay, that's the moral of the story. You have 10 minutes to teach you stuff. There is one other method that can help you for an educated guess, for designing PID. Now, I usually keep that as optional, but we talk, and Brett is actually very useful in his other courses, like if he knew that. Because when I say optional, students don't study it, right? But when it's not optional, you have to study it. So we're making it not optional, so it means that you have to do it. Thanks to Brett. You can give him thanks later. But I also think it's very useful, but you will probably not use it for all the systems. So that's why I brought it last, after you exhausted all the other ways. But this will give you a very good start in guessing your values. Now, this is called Ziegler-Nichol's method. How many of you have heard of that? None? Great. I'm just gonna go over the basics. We're gonna probably solve an example using this. I just want you to be familiar with. All right, so there are two methods in Ziegler-Nichol, sorry. Open loop and closed loop method. In open loop method, you take the controller off of your loop, so off, open loop is not in the loop, and then you solve based on that. In the closed loop method, you're going to actually put your controller in there, you assume something, and then find the values for it. That's basically the difference and why it's called open loop and closed loop. in the open loop method, you're gonna say that, hey, let's find the response of a system without a controller, an open loop. So open loop, meaning that there's no controller in the system. It could still be a feedback loop system, all right? You run and you see the response is gonna look like something like this, which also resembles a first order system response, right? Something that doesn't have overshoot or a big overshoot. If it's a small overshoot, it's fine. If your response looks like that, you can measure R and delta T. R is the slope of the tangent line and delta T is the intersection of the tangent line. You measure these two, then you use this table, very useful table, and you guess values for Kp, Ki, and Kd. That is a very good start to design your controller. You will have less iteration to get to the final Ki, Kp, Kd. So this depends on the response of your original system. If it looked like first order or if you didn't have a big overshoot, you can do this and use that. This is the open loop method. For the closed loop method, so if the response didn't look like first order, you cannot use this method. So you might be able to use the closed loop method. For closed loop method, you put the controller in this loop, but you only assume it to be a key controller. So you give Ki and Kd 0. So you only have Kp, like a gain, right? And then from there, you will plot the response and you increase the gain so much until you will see an oscillation. So when you have oscillation in your response, what does it mean? Where are the poles of your system at this one of them? Very close or on the vertical axis, right? So we want to get to the point of instability. So we're trying to find what gain will give us instability. So you want to be on the border. So you don't want to pick that gain, but on the border. So this is your, what is it called? What do I call it? Ultimate gain. So this is ultimate gain. You call it Ku. And then from the response, you go and measure the period for that. So from those two numbers, then you use this table to find Kp, Ki, Kd. So basically run the system until it's unstable, almost unstable. So maximum gain. And then you can find Pu from 2 pi over omega n. Omega n is just the frequency. So if you can find the frequency of the system from other ways, you just plug it in. But it's easier to just measure. Since these are all estimation, you don't have to be very accurate, right? You find a number is very close. But then the cool thing is your first Ki, Kd, Kd are going to be very close to your final solution. Now, Ziegler-Nichol method is very good for coming up with values that will help the system to reject disturbance itself. So when we are designing a controller, we usually check the trackers, right? And track. But this method will guarantee that it will also reject disturbances as well. Okay, so you might find the KIKT from this method not equal to what you find from other methods. The reason is that, again, as long as it meets your requirement, it doesn't matter. It's a good controller, right? Just different methods. So, I'm going to give you 5 minutes. So that's it about PID controller. You can do your homework for all the questions. Next week is exam on Friday. I just had a brain tumor when I was writing my